Good morning, dear students. Today we are having the 10th practical lesson. On previous practical lessons, we calculated double integral in rectangle coordinate system, and today we will calculate integrals, double integrals in polar coordinates. So let me share my screen, and then I will explain you why do we need them. So I will remind you a little bit. Just a moment. So how do we move to the polar coordinates? We do the following thing. So the following formula: x equals rho cosine of phi, and y equals rho sine of phi. And the integral in such case looks like on the right side, and the function depends on rho cosine phi and rho sine of phi, and multiplied by rho. And also, as we can see here, we have d prime. So it means that the region D is given in another way with using variables rho and phi. So when they're used, when we have a round or elliptic region of integration. So first of all, let's have some practice with transferring to polar coordinates without calculating integrals. We will just move to polar coordinates. So we have the following integral on region D. So f from xy dx dy, and the region D is the following circle: x square plus y square equals to x. Yeah, so this is a circle, but it has the center not in x, not in the beginning of coordinates. So x square plus y square equals to x. So its coordinates are so the coordinates of the center are 1, 0. So how the region actually looks like. Okay, now let's move to polar coordinates in this equation of the circle, and what will we have? So rho square by cosine square of phi plus rho square sine square of phi equals to rho cosine of phi. Now we will simplify this expression. So what do we have in the left side? Rho square. And we also can cancel rho. So we have the equation rho equals 2 cosine of phi. So this is the upper limit of integration. What is actually rho? Rho, it is a distance from the beginning of coordinates to the curve. And phi is, just let me remind you, phi is the following angle. So between x-axis and this, and so this is phi angle. Let me clear it. And in our case, we can see that phi changes from minus p over 2 to p over 2. And rho actually changes from 0 to 2 cosine of phi. And now we will rewrite the limits of, now we will rewrite the integral with the new limits. So phi from minus p over 2 to p over 2. And here d phi. And the inner integral from 0 to 2 cosines of phi, f from rho cosine of phi, and rho sine of phi, multiplied by rho d rho. So this is our integral in polar coordinates. Any questions about this exercise?
Why phi in these bonds?
Phi?
Yeah, phi.
Okay, so as I explained, phi is the angle between x-axis and just another array. So the first quarter is so corresponds values of phi from 0 to p over 2. And if we go here, so from minus p over 2 to 0. So that's
Yeah,
such limits of integration. Have I answered your question?
yes, thank you.
Okay, more questions? Yeah, by the way, let me remind you that you shouldn't, yeah, don't forget to multiply by rho when transferring to polar coordinates. It is important, so don't lose it. And now let's move to the next exercise. Exercise 2. Okay, let me erase these limits of integration. I guess, if I'm not mistaken, we again will have so just transfer into polar coordinates. So yeah, we need to go to polar coordinates again, and we have the following limits of integration. Yeah, okay, let's start with the A. So it is bounded by circles given by following equation. X squared plus y squared equals 4x. And x squared plus y squared equals 8x. Again, let's go to polar coordinates in these equations. By the way, and lines y equals x and y equals 2x. It's important. So let's go to polar coordinates and we will see what happens in these equations. Yeah, and also let's plot this region. So x square plus y square equals 4x, and then x square plus y square equals 8x, then y equals x, y equals 2x. So actually we have the following segment. So this segment, and by the way, let's look at this plot. It looks better. And also here we have coordinates of the circles, but really we don't need we don't need the centers of circles when moving to polar coordinates. That's just for easier plot. So the first equation, rho square cosine square of p plus rho square sine square of phi equals 4 rho cosine of phi. So then, when we simplify this equation, we have rho square equals 4 rho cosine of phi. And finally, we will have that rho equals 4 cosine of phi. Analogical to the second equation, yeah, I lost rho, but I will return it. Here we change 4 to 8, and actually that's all what we will change here. So these are limits of integration for rho. And what about phi? So y equals x, it means that rho cosine of phi equals rho sine of phi. We can divide both parts by 0, or by rho, sorry, we cannot divide by 0, of course. We can divide by rho because we know that it's not 0. So cosine of phi equals to sine of phi, and it means that phi, by the way, tangents of phi equals 1, so phi equals p over 4. Phi equals p over 4. So found the limit for phi, and again another limit for phi will be found from this equation. So 2 rho cosine of phi, and here 2 cosine of phi. So tangents of phi will be equal 2. And then it means that phi will be equal arctangents over 2. Oh, Greek symbols. So this is not a table value, but phi can have such values. So what are the limits of integration? In this case, so for phi, the phi changes from p over 2 or p over 4 to arctangents over 2. Yeah, such hotkeys are a little bit not convenient. And phi changes, rho changes from 4 cosine of phi to 8 cosine of phi. So here are our limits of integration. And now let's substitute them into the integral. So arctangents of 2 from dphi from arctangents of from p over 4 to arctangents of 2, and rho is from 4 cosines of phi to 8 sine of not sine but cosine of phi. So this is our integral in polar coordinates, and yeah, we don't know the function, but actually these integrals are equal. Any questions about this exercise?
No questions.
Okay, no questions. So then moving next, actually, yeah, 2b is analogical to a. And now we will skip it, but then we will continue. Yeah, we will convert yeah, again integrals to polar coordinates. So we have task 3. So what will we actually have to do? Again, we will have to move to polar coordinates, but yeah, let me leave something like it must be. So let me clean our board a little bit, and then we will continue. Yeah, I have some problems with my mouse, and touchpad is not really convenient. Okay. So let me write down integrals. So we have the following limits for x. So x from 0 to r, and y from 0 to r square minus to square root of r square minus x square. So if previously we received limits of integration with the equation of the region of integration, now we build the region of integration from these limits of integration in rectangle coordinates. So let's plot this region with using these limits, and we will understand actually what is the region here. So let's plot this square root. So r square minus x square. So we have such a semicircle. Yeah, and by the way, y is less or equals, and also y is greater or equals than 0. And now, what we also know about x, that x is between y and r. So it is the quarter of the round. So now we from this plot we understand that phi changes from 0 to p over 2 and rho changes from 0 to r. So we have updated limits of integration. So the following integral. Yeah, and it is much more convenient than integrate such square roots. Agree? Any questions about this exercise? I guess that no question.
No.
So now let's have some practice with this region. So now with B also. So it is a little bit more complicated, but I guess that no such complicated. So x from r over 2 to r, and here to r y minus y square. Yeah, and by the way, we have to change order of integration here. And now let's plot actually this graph. So yeah, and by the way, x is less or equals, and x is greater than 0, greater or equals than 0. Then what about y? We know that y is so has values from r over 2 to r. So between these values. So actually we can also plot these straight lines. So we can see how it changes. So let's transform also these limits of integration. So it will be equal to r sine of phi minus sine square of phi. So what does it mean actually? Yeah. And we need to solve following, actually the following double inequalities. So r over 2 is greater, okay, so y, so will be between these values. So we will have to solve such inequalities, double inequalities. And what about x? Yeah, so from 0 to this expression. Yeah, and by the way, I lost rho. Okay. So what do we know now about it? We can simplify this inequality a little bit. So we can, what we can do. Okay, let's start first of all with this inequality. It will be better. So I will change, I will raise it to square. So rho square cosine square of phi will be equal this expression without square roots. Then we will receive that, when we move this, rho square everywhere, sine square of phi. So we will receive the following stuff. So it will be rho square is greater or equals than 2r rho sine of phi. And now we can also cancel rho, 1 power of rho. So we have that we received that rho is less or equals that 2r of sine of phi. And if we plot it here, so equals to r sine of theta here. So actually this circle, so limit for one of limits for rho. Okay. And now moving next. So we also can see from the graph that phi is between 0 and p over 2. So it's absolutely in the first quarter. And what else? Yeah, by the way, rho cosine of phi So we can see that, yeah, by the way, what about these equations? So rho sine of phi equals to rho. Yeah, let's plot and solve graphically. So equals to r. And if it equals r over 2, we will receive the following straight line. So we can also figure out here that yeah, rho is greater or equals than r over 2 sine of p. So let's now write down limits of integration. So phi changes from 0 to p over 2. And the rho changes from r sine over 2 sine of phi to r of sine of phi. So done. And now let's substitute this limits of integration into the initial, not into the initial integral, but into integral and polar coordinates. So rho phi didn't change. And what about rho? So it changes from rho by r by 2 sine of phi and to rho sine of phi. So that's it. Any questions about this exercise?
No questions.
Okay, no questions. So let's move to the next exercise. I guess you had enough practice with moving to polar coordinates. So now let's start solving integral. Let's start calculating integrals in the polar coordinates. So for A, we have the following integral. So D, and yeah, let's first of all write down the integral. And here you will just understand how polar coordinates really can be helpful. So D is this bounded by a circle of radius r equals 2, and the center is at the origin. So actually this is so we will have the following around. So the region is the following. Yeah, it's quite simple. So let's check this. Yeah, from this equation, x square plus y square is less or equal than 4. So it will be transformed to, yeah, let me write again in details. So rho square by cosine square of phi plus rho square by sine square of phi, and less or equals than 4. So what does it mean? It means that rho square is greater or is less or equals than 4. And we actually can write down limits of integration. So 0, so v changes from 0 to p. And what about rho? Rho changes from 0 to 2. And now we can write down the, yeah, by the way, yeah, let's also transform this expression. So what would be equal? It will be equal to 4 minus rho square. So we will rewrite this integral. So from 0 to p d p, and integral in the integral is from 0 to r. So let me copy and paste this expression, and don't forget to multiply by rho. D rho. And as we can see here, we can split this integral to the product of two independent integrals. So let we do it. So in this case, we have 2p multiplied by this integral. And here we will use differential entry technique. So we have minus p, and here we have the differential over this expression. And now let's integrate. So minus 2p over 3. Yeah, 4 minus rho square. Okay, let me copy and paste it and remove what is redundant. and with the substitutions from 0 to 2. If I substitute 0, if I substitute 2, I will receive 0. If I substitute 0, I will receive minus 8. So minus 2 multiplied by 4. So we will receive 16 p over 3. So it's the task became quite easy, right? With moving to polar coordinates. So just imagine integration of integration by y from minus square root to square root, a lot of square roots in which you can easily make a lot of mistakes. But polar coordinates really simplify the solution. Any questions about this exercise?
No questions.
Okay, if no questions, let's solve also B. And then we will have a break. Again, one more example how polar coordinates are useful. So we have the following integral where we already have limits of integration. Okay, let me erase it completely. So we have the following integral. So x is changing from minus r to 0. And y changes from 0 to square root of r square minus x square. And here what do we have? We have logarithm of 1 plus square root of x square plus y square, and the square root in the denominator. dy. And it is under the integral here. Okay. Again, let's plot the region. So y is less or equal than square root of r square minus x square. Yeah, y is greater or equals than 0, and x from minus r to 0. So it is the second quarter. So from this plot, we can understand that phi changes from p over 2 to p. And rho changes from 0 to r. And what about these expressions? Yeah, so let's simplify them. So we have here a logarithm of 1 plus rho square. And this 1 plus rho, sorry. 1 plus rho, and this expression will be equal just to rho. So let's move to the integral with the new limits. So from p over 2 to p d phi and rho from 0 to r. And what do we have? Logarithm of 1 plus rho divided by rho. And also we need to multiply by rho, by this Jacobian of transition. And what can we see here? That we can first of all simplify rho. So to cancel rho in numerator and denominator. And also we can split again this integral to the product of the separate integrals, so we can separate the variables. So let's do it. Okay, and now let's calculate two integrals separately. So I1 equals this integral, and it will be actually equal p over 2. And what about the second integral? We will calculate it by parts. So we will remember this formula a little bit. So in this case, u will be equal to the logarithm. Then du equals d rho by 1 plus rho. Then dv equals dx, and v equals x. So we
But
have...
why dx?
Yeah. Sorry. Yeah, thank you for your attention. Just automatically. So now everything is correct. So rho multiplied by logarithm of 1 plus rho with the following substitutions. So from rho to 0, or from 0 to r. Stop. I misclick. And minus the following integral. So from 0 to r. So r plus by 1 r over 1 plus r plus rho. Sorry. So what do we have here? So if we substitute r, we have r a logarithm of 1 plus r, and if I substitute 0, I have 0. And minus, yeah, let's simplify this integral. It will be actually equal, yeah, if I, so if I extract the whole part, it will be equal 1 minus 1 over 1 plus rho. On stop. Yeah, correct. So copying and pasting this part and minus the following antiderivative. So with the substitutions from 0 to r, rho minus logarithm of 1 plus rho. So if I substitute everything, I will receive the following expression. So rho minus logarithm r minus logarithm of 1 plus r. And if I substitute 0, I will receive 0. So what is the final answer? It will be equal p over 2 multiplied by this expression. So maybe it can be simplified in some way, but actually we will not do this arithmetical stuff. What was required is to calculate the integral. Any questions about this exercise? Oh,
No.
okay, if no questions, let's have a break for 5 minutes. And after that, we will continue calculating double integrals in generic polar coordinates. And also we will use double integrals to calculate the area, mass, and so on. And now have a break. Okay, let's continue. So now we will calculate the double integral in so with using generic polar coordinates. So it is actually almost the same as polar coordinates, but yeah, we substitute x as a multiplied by r cosine of phi, and y equals b sine of phi. So actually it is the special formula for elliptic region. So a and b are semi-axes of the ellipse. So it becomes easy to calculate such integrals. But let me simplify. Let me raise clear the board. Yeah, and instead of rho, we multiplied by AB rho. AB rho. So this is the Jacobian of transition. Transfer Jacobian. So, and now the exercise 5 is the following. So we have the following integral d and the following expression y minus x square over a square minus y square over b square dx dy. So now we will yeah, actually we already can write down limits of integration. So it is the ellipse. So yeah, by the way, let's write down the equation of the ellipse. So x square over a square plus y square over b square equals 1. So if I substitute generic polar coordinates, what I will receive? So a square rho square cosine square of phi divided by a square plus the analogical stuff to the semi-axis around the semi-axis along y. So b square by rho square by sine square of phi and divided by b square equals 1. So if I continue simplifying, so first of all we can cancel a and b square. And then we actually will receive that rho square equals 1. So it means that rho changes from 0 to 1. And p obviously changes from 0, phi changes from 0 to p. and row from 0 to 1. And what about this expression? So it will be equal 1 minus row. 1 minus row square. So, writing down the integral. So from 0 to p, d phi, and row from 0 to 1, and this expression 1 minus row square, and multiplied by a, b, and row. So let's simplify this integral again. So what can we do? First of all, split it. Yeah, let's move out. Let's move constants out of integral, and also split this integral by the product of independent integrals, because we can do it in this task. And what do we have? So this integral will be equal to p. So 2p ab by this integral. And here we can move this, so we can move row under differential. Erasing a row, and here we will have minus PAB. So here we have minus 2 PAB over 3, and again, let's just copy and paste and then erase what we don't need here. So this is our antiderivative. Yeah, and some substitutions from 0 to 1. So if I substitute 1, I will receive 0. If I receive, I will receive 0. If I substitute 0, I receive minus 1. So the final answer is 2 or 3 PAB. So that's it. Any questions about this exercise?
I don't understand why we have these bonds for phi and rho.
Okay, phi from 0 to 2p, because yeah, so if I plot the ellipse,
Yeah, I understand from
yeah,
the graph.
and what about rho? Rho equals 1 actually received if I substitute generic polar coordinates into this equation. And finally, we have rho square equals 1, so it changes from 0 to 1.
Okay, I thought that rho square 1, that it must change from minus 1 to 1.
No. Rho is a radius. So it is radius, so it cannot be negative.
I understand. Yes, thank you.
So yeah, it can be 0, but it cannot be negative. So this is the idea of polar coordinates. More questions? Okay, if no questions, let's continue calculating integrals, and we will have the exercise where we need to calculate the area of the figure. So the figure will be the following. So it is a point figure that bounded by following lines. Rho equals 2 cosine of phi, and rho equals 4 cosine of phi. Actually, so we have already polar coordinates here, so we don't need to transform circles. And yeah, by the way, we have already graphs of this. We have a graph of this region. So the area will be calculated by the following formula. So let me remind you that we integrate 1 by region D, and it will be a value of this integral. Okay, what can we see from this graph? That p changes from minus p over 2 to p over 2. And what about rho? Rho changes from 2 cosine of phi to 4 cosine of phi. So now let's transform. Let's set limits of integration. So from minus p over 2 to p over 2. And rho depends on cosine of, it depends on phi actually. Yeah, and don't forget to multiply by rho. So the integral will be the following. In this case, we cannot split it by 2 independent integrals, but actually it's not complicated for us to calculate it. So we have the following integral. So 1 over 2 rho square with the substitutions from 2 cosine of phi to 4 cosine of phi. So let's move these expressions here. Moving 1 over 2 out of brackets. And what we actually will receive. So 16 cosine square over phi minus 4 cosine minus 4 cosine square over phi. And erasing this stuff, so it will be the following integral. So 12 cosine square of phi. Yeah, by the way, we can multiply by 1 over 2. Yeah, we can even move 6 out of brackets, out of the integral sign. So, and it will be our integral. And also what we can see from the integrand that it is an even function, so we can simplify it with calculating from 0 to p over 2 and just multiply by 2. Then, yeah, now let's downgrade the power. Let's reduce the power, and what will we have? So, 1, yeah, and it will be multiplied by 6. So 1 plus cosine of 2 phi. So now integrating it. The antiderivative will be the following. So substitutions from 0 to p over 2. So p plus 1 over 2 sine of 2 phi. So if I substitute p over 2 here, I will receive p over 2, and if I substitute here, I will receive 0. So sine will be 0 for both of these values. So the final answer will be 3p. So that's it. Any questions about this exercise?
No questions.
Okay, no questions. So moving to the next exercise. So we need to calculate the mass of a flat plate bounded by the following area. So actually this is the quarter of the round where x and y are positive. So let's plot it. Of course, x square plus y square less or equals than 4, and both x and y are greater or equal than 0. So y is greater or equals than 0. So this quarter of the round. Yeah, let me erase these formulas, and we will continue to the new task, on the new task. So, yeah, how to calculate the mass? The following formula. So we need to calculate the following integral. We need to integrate the density. We need to calculate. We need to integrate the surface density in this region. So, and in our case, it is equal to x square. So, yeah, x square, not x square, x cube. So x cube, it will be equal to rho cube by cosine cube of phi. And yeah, by the way, from the graph we can see that p changes from 0 to phi, not p, but phi changes from 0 to 2p, to p over 2, sorry. And rho changes from 0 to 2, because the radius of the square equals 2. So how will look like the integral? So from p from 0 to p over 2 d phi, and the inner integral is so from 0 to 2 rho cube by cosine cube of phi multiplied and also multiplied by rho d rho. And now let's simplify this integral. So what can we see here? That this integral can be split to the product of independent integrals. So we can move cosine cube phi into the outer integral, and yeah, also simplify the inner integral. Yeah, and just rewrite it as a product. So product of these integrals. So we integrate rho in power of 4. And let's calculate both integrals separately. So I 1 will be equal this integral. So how can we simplify it? Cosine of phi by multiplied by 1 minus sine square of phi. Then yeah, we will move cosine of phi under the differential. And what we will actually receive? So 1 minus 1 over 3 sine of phi with substitutions from 0 to p over 2. And I received sine cube, sorry, sine cube of phi. It's important, yeah, and phi here actually. So if I substitute, I will receive p over 2 minus 1 over 3. So this is the first integral, and what about the second integral? So 1 over 5 rho in power of 5. And with the substitutions from 0 to 2. So 32 over 5. And the final answer will be the following. So this stuff multiplied by 32 over 5. So that's it. Any questions about this exercise? Stop. Sine of phi. That was a mistake. Yes, sine of phi. So 1 minus 1 over 3. So it will be 2 over 3. Yeah. I just forgot that we integrate by sine of phi. So it equals 64 over 15. So calculated the mass. Any questions about this exercise?
No questions.
About the whole lesson, about previous lessons, maybe?
For now, no.
Okay, if no questions, so we will finish. Have a nice day, stay safe, and thank you for your attention.
Thank you. Goodbye.
Thank you.
Goodbye.
Goodbye.